Hello and welcome back to the Carbon Nanotube Intro to Houdini mini-series where we're making these structures that you can see in the background behind me. If YouTube has somehow recommended this part 3 video to you and you haven't seen part 1 or part 2, don't worry about it. You can always click up here in the I button pop-out thingy for part 1 or in the video description for parts 1 or part 2, or feel free to check out this part 3 as a standalone thing, totally up to you. But let's just jump right into Houdini and get started. So just to recap, last time we created this buckyball structure, which is a 60 atom carbon nanosphere thing here. And we discussed geometry in Houdini, points and primitives and how to manipulate them. I'll try to put a starting file with this buckyball here in the video description so you can kind of follow along in this part from where I am here. It's worth mentioning that unlike in Maya, where it's really important to have that project structure set up right at the beginning where you can save your files in the right places, in Houdini it's less important. You can just kind of save these Houdini files wherever it makes sense on your hard drive if you're wondering about that. And the project structure doesn't come into play as often. And especially in this project where we're not dealing with very much external files, then it's very simple to work with. Houdini does have project features for working on larger projects, and it's worth looking into those if you're interested in doing that sort of thing. I'll give you one tip that tripped me up coming from Maya to Houdini. In Maya, your current project, which determines where certain files get saved or loaded in from, is saved in your user preferences. So every time you want to switch a project, you got to go File, Set Project, and update your user preferences for what you're currently working on. In Houdini, you can set a project which can be used to determine where to save and load files from. That folder path is saved with the file. It's called the job variable, incidentally. So if you switch projects, you don't necessarily have to set the project as well, assuming that had already been done in that file. So just one step shorter if you're switching projects. So I haven't completely explained how all of that works. I didn't want to get into it too much in this video, but I did want to flag it up as a point of difference in case you run into that, and then you can look into that further. So very quickly, a recap here. We created spheres, which we copied onto points to represent the atoms. And then we also had these short polygon curves that we used to create bonds. And then we merged them together and colored them black. And that was our buckyball from last time. In this lesson, we're going to expand on our buckyball and create a full nanotube. Okay, the rest of our carbon nanotube, we're going to be creating this cylindrical structure. And this picture is of a multi-walled carbon nanotube. We're just going to create a one wall. So for example, this blue cylinder, you can imagine. So it looks like this kind of hexagon grid that's kind of in a tube shape. And unfortunately, we can't rely on a simple platonic solid like the soccer ball that we did last time to figure out where the atoms are going to be. Incidentally, a soccer ball is not a platonic solid. It's an Archimedean solid, a truncated icosahedron, but Houdini puts it inside of the platonic solid node. So anyways, but we can't use one of those. So how are we going to create this hexagon grid in this tube shape? Well, as always in Houdini, there are a variety of ways you could do things. Perhaps you could imagine creating some sort of zigzag pattern around one kind of circle of the tube and then copy that in one direction and kind of offset it or have it arranged in a certain way so that it stacks up in the right way. That would be one option. What I ended up doing is creating, and what we're going to be doing in this video, is creating a flat hexagon grid, not infinite, but a tileable grid of hexagons, and then roll those up into a tube. So we're going to create a flat hexagon grid, evenly tiled, and then we're going to roll that up. Okay, so let's just jump up with U key and get back up to our object level here. And I'm going to rename this from buckyball to nanotube because we're actually going to be doing all of our work in this same space for reasons that will become clear later on in the video. So we're just going to shift all of this to one side and start working in this area over here. And again, if you're opening up the files and you can't see anything, it's all blank, you can always hit space F or space H with your mouse in the network view here, and all of the nodes should zoom in back into view. Now, making tiled hexagons, there's probably a ton of ways to do this in Houdini. In fact, I know that there are a ton of ways to do this in Houdini. I went searching and I found a bunch of ways to do this, a tiled hexagon grid, but I was surprised at how many of them did not create perfect hexagons, like regular hexagons with all of the edges the same length around. And we need that for our carbon atoms to have equal bond lengths. So there was stuff squished, there was stuff stretched, there was stuff inset. So I like to be mathematically perfect with this kind of thing when I can, and I know that I can here. So we're going to do this in a slightly mathematical way. It's going to be a little bit technical, but I'm going to explain our way through it. And if you discover a different way to produce the same result that's much easier, that's fantastic. Explore this idea on your own. I'd love to see different people's takes on how to make hexagon grids. So what we're going to do is we're going to be starting with a tube. So we're going to hit tab, type in tube, and we're going to hold down R and click on the node to set the display flag. You could also select the node and then hit R, or just click this blue eye icon, various ways to set the display flag. But what that means is now we're looking at the result of that node in the viewport, and we can see our tube. Okay, so this isn't quite the tube that I want. I want a hexagon tube. So we're going to change the primitive type to polygon, and immediately we have this kind of faceted sides. And instead of 12 columns, I just want 6. There you go. There's our hexagon. So now what we're going to do is we're going to tile this in this direction, in that direction, every which way, and get our grid of hexagons. Okay, so from last time, remember that our soccer ball, we wanted the bond lengths to be 1.42 angstroms in length. So essentially what that means is that these points need to be 1.42 units apart. How are we going to do that with our tube? You might already know the answer to this, but I'm just going to explain this mathematically so that it makes sense for everybody. So I'm going to go into the top view. So you can either click perspective, set view, top view, or space 2. And I'm going to press space F to frame selected. And if we don't see anything, it's possible that it's because we're in shaded view, and for some reason you can't see the edges of infinitely thin planes in shaded view. So we'll go to wireframe. Boom, there we go. There's our hexagon. And we could also turn on the display points so that we can more easily see where the corners of our hexagon are. And just so I can explain the math here, I'm going to take a screenshot and draw on the screenshot. Okay, so in Houdini, the radius of the tube is defined as the distance between the center to any given point here. So this distance here is the radius. We're interested in this distance, but you'll notice that in a hexagon, there's these kind of embedded equilateral triangles. And an equilateral triangle has equal edges. So we know that this length here is the same as this length is the same as this length. And there are 6 equilateral triangles embedded in any given hexagon. So now that we know that this edge length is the same as this length, then we can just set our radius to 1.42 and we should be good to go. Okay, so 1.42. Now if we go back to my perspective, space 1, and kind of go around here, we can see that we've only changed one side of the hexagon, and that's because in Houdini, this radius, there's 2 radiuses, radii, one for the start and one for the end, so you could have flared tubes and cylinders and that sort of thing. So what we can do is we can just copy this value and paste it in here. Now we're going to see something that's very cool and powerful and a great way to make things more procedural. What do I mean by procedural? Well, you can kind of think of it like if you wanted to go back later on and make a change to any of these parameters, is it going to break things or cause problems for your final result? When you make things procedural, it's very easy to make changes or make variations to the things that you're making and have everything still work properly and get the result you want. So the category of thing that we're going to be doing here is called expressions. And I know that sounds scary, but don't worry, we're going to take it very slow at the beginning. The simplest version of that is something called a relative parameter reference. Okay, that doesn't sound any less scary. I know. But it's actually going to be fairly simple here. The first question you need to ask yourself out loud when possible is, what do I want? I know that's a big question, but just narrowing it on the scope of this Houdini problem here, what we want is for whenever we change the radius, we want everything else that relates to that radius to get updated automatically. Like for example, the second radius here. So the start radius gets changed, the second radius gets updated. Yes, we can do that manually, but that can be time consuming if you're making lots of changes or you might forget. So it's better to be automatic when you can. So I'm going to set this back to 1, the original value, and we'll see how this works. We just right click on this parameter, go copy parameter. And then here we could go paste values, and that's going to paste the values just like copy and paste. But instead of that, what we want to do is we want to right click and go paste relative reference. Okay, it looks like it had the same result, except we see a whole bunch of weird stuff going on here. So we have a blue-green color in the background here, and that's to show that we've made this relative reference. And what this is doing is it's referring to another parameter. So CH here is short for channel, and channel is kind of like the same thing as parameter, except we usually reserve it for when there's more things going on, like we have an expression in the parameter, or if there's keyframe animation, just more things going on with it. So you can think of a channel as kind of like a parameter. So we can say that this is like the radius channel. But in this case, what we're doing is we're just saying, okay, get the value from the parameter called rad1 and store it here. So what's parameter rad1? Well, if we hover over here, this radius, we can get the names of the parameters. You can see it says parameters rad1, rad2. So this is rad1, this is rad2, radius 1, radius 2. A little bit of mouse work here that you may want to practice and remember as useful sort of tools for working in the parameter view. So if we left click on the name of the parameter, we're going to toggle between two states. One is showing the end result, the values here. So we can see 1.42, 1.42. Those are the final values. But if we click on it, we can see what's driving those values. So in this case, it's just a float value, 1.4. And in this case, it's just a slight precision error. It's essentially 1.42. And in this case, it's our little relative reference to another parameter that's driving that value. So we're just toggling between those views. Another thing you can do is you can go Control-Shift, left mouse button, and that's going to remove any expression or animation on there and just leave that current value there. So that's kind of like baking it in and deleting the channel information, just getting that value back. Another very useful one is Control middle mouse button, and that's going to revert back to the default value. So you can see that I've by Control middle mouse clicking in the radius 1, we're setting this back to its default value, and this one just gets updated because, again, we have a reference to it with our channel reference. So if we're going to set the columns back to default, Control middle mouse, and that's going to go back to the default value of 12. It's a very, very useful thing, and I wish more 3D applications did something similar to that. You'll also notice that the non-default values are kind of bolded here. If you've noticed that, like this one is bolded. If we put this one in 1.42 back here, those get bolded. That's showing what isn't a default value. That's very useful because it lets you easily see what you've actually changed on a node, which is really good for troubleshooting and other things. Again, I wish more applications did that kind of thing. And this one, I didn't actually even know this was a thing until I started looking at the options here. But if you do Shift right mouse button, it's kind of a toggle between your two most recent values in that parameter. It's kind of like doing a Control Z, Control Y kind of toggle, but it doesn't even have to be your most recent change. Like I could edit this one, and this one is still going to toggle between those two states, and this one would toggle between those two states. One more thing you do with the mouse in the parameter view that we've seen before, but I'm just going to repeat it for the sake of clarity here. If you middle mouse button, then you get this virtual slider where you can change the precision of what you're actually changing. And then by holding down, continuing to hold down the middle mouse button, you can drag left and right and then go down to a smaller precision value and kind of use this slider to make whatever changes you want to those values. So back to the expressions here. So we've got this value locked to this value, so it doesn't matter what we put in here, it's going to get updated here. Now, if you're super smarty pants, you might have noticed that there's actually another radius parameter here. That's just one value that we could change, and that's just going to change the whole radius, which is kind of what we want. So we didn't even need this. Yep, that's fine. You can totally do that, but I was trying to use this as a teachable moment. So that's why I did it that way. But now we're actually going to do another expression that's very slightly more complicated. So that's why I started with this very simple value. And that's something that we're actually going to be using here. And the idea here is we want to move this tube up or down so that these points are sitting in the exact plane where y equals 0, essentially, like on the ground plane. So again, asking ourselves out loud, what do we want? Well, we want to move the tube up essentially half of its height so that it's sitting on the ground plane, half of its height. Well, we can see we got the height here, and this center value determines how much sort of offset in y the tube is. So basically we want to do half of the height in here. So yeah, we can manually put in 0.5 and that's going to do what we want, but maybe we're going to change the height later. We're not, but it's good to think about this in a procedural way. So how would we do that? Well, we could do copy this height parameter, paste a relative reference here, and now we can see we've jumped up a full height. We don't want to jump up a whole height. We want to jump up just half the height. So we're going to take this value. So this is going to return the value of the channel parameter, height, and we're going to divide by 2. There we go. And now we've got it jumped up half the height, so no matter what we put in the height, it's going to stay locked on that ground plane. And you'll notice that this is a different color now. It's this light blue instead of this dark blue green. And that's because we've made a full expression. It's not just a simple parameter reference, but a longer expression. And just so we can confirm that value, I'm just going to go up here and split the plane top and bottom like we've done previously and open up our inspector, the geometry spreadsheet. And we're in the point spreadsheet. We can see that for half of the points, points 6 through 11, and we can turn on our point numbers here if we want. 6 through 11 are sitting at exactly a y position of 0. All good, fantastic. So the other reason to use expressions here is that you're getting rid of what we call magic numbers, which are numbers that we don't know where they came from, what do they actually mean, why did we use them. You're telling other people or your future self why you did what you were doing. If we just put 0.5 in here, we'd be saying we want this value to be 0.5. But what we're actually saying is we want this value to be half of the height, which is much more informative. And when you start getting a more complex node network, you're easily going to forget the reasons for the decisions that you made. And so when you have things like these expressions, they can remind you, oh yes, I was thinking about it in this way. So that was a lot of talk about expressions. We're going to move along now. And basically we only want this bottom part of the hexagon when we're tiling our hexagon grid. We don't really need it to have any height. So what we're going to do is get rid of the top half. So we're going to put down a blast node, which is a node that we use for removing geometry components. Now by default, it gets rid of everything because it's basically saying you haven't put anything in here, delete it all. There's a few different ways that we can specify what we wanted to delete. We could specify the name of a group. And if you'll remember, like down here, we had two groups. There was the atom prims group and we had the bond prims group. So for example, I'll just shake this to bring it over here. If we wanted to delete just the, select it here, delete just the atom prims, then we can see that we're, go back to our smooth wire shaded, we can see that we've deleted the atom primitives. And we could also invert this. So delete non-selected means delete everything but the atom primitives essentially. Shake this and bring it back here and see what we can do here in the with our tube. We can also specify a manual selection, which is less procedural, but sometimes it's pretty safe. So that's what we're going to actually do here. One thing that really often trips me up is this group type here. We can let Houdini guess what kind of component that we want to delete, but it's better to be explicit when we can. So I want to go down here and click points so that we're deleting points. And if we select this arrow here, then it's going to let us choose from the viewport which points we want to remove. So I want to remove just these top ones here, which are points 0 through 5. And you can see that it's put in here 0 to 5. So we've deleted those points and left just these ones here. And incidentally, because we deleted those top ones, the primitives that were attached to it get removed as well. It's worth noting here, you'll notice that we still have points 0 through 5, and that's because when we removed the original points 0 through 5, these ones got a new number assigned to them. So they're not fixed point numbers, they kind of get updated depending on how much geometry there is. So sometimes you might want to mark something for deletion and then delete it later on, so you're not like shifting around those point ranges and stuff like that. Something just to be aware of. So now we've got these hexagon points and all we need to do is tile them. So we're going to be using some more mathematics for that, which is going to be fun. So I've jumped into my top view here, and what I'm going to be doing is using a copy and transform to make a whole bunch of copies of those hexagon points in one direction here. So copy and transform. I can click on the dot here to automatically connect it up and then put the display flag on here. And we can make a whole bunch of copies here. Maybe 200, but they're all sitting on top of each other. So we want to space them out, offset them a little bit. So this one, we're going to be offsetting them in the Z direction, which you can see from this little axis down here is in this direction. So we're going to go in here and we're just going to start spacing them out until we kind of get them so that they're somewhere in here. We can go a little precision. And now you can eyeball it, but I don't like to eyeball things if we can make it mathematically perfect. And like I said before, we can. So that's what we're going to be doing. But we're looking for a value somewhere around 2.5. So this is going to be a little bit of geometry lesson. This may be complete review for some people, and this is going to be a little bit strange and uncomfortable for other people, but we're going to get through it. So I'm going to go back to the tube here, and I'm actually going to go into wireframe mode, and I'm going to take another screenshot and draw over it. So I'm going to hide the geometry spreadsheet by clicking this down arrow here. We can always bring it back, but I'm just going to hide it. So basically what we want to do is we want to be moving this hexagon down this distance from this edge to this edge so that we perfectly can tile it in this direction. It's a bit easier mathematically to look at half of this distance and then double it at the end. So what we're going to be doing is we're going to be looking at this relationship to here. Is that the radius? No, it's not quite the radius because this is the radius. So I'm going to put a different color here, and I'm just drawing with my mouse, so apologize, it's going to be ugly. So we've got, I'm going to use W instead of X because we have an X axis and I don't want to get that confusing. So W is the distance, actually we want twice the distance of W to move our hexagon down. But we do know that this is the radius. I do recommend brushing up on a little bit of high school geometry because it turns out in 3D graphics you encounter triangles quite a lot. So what we have here is a right triangle. We've created a right triangle from this distance, and the radius as the hypotenuse. And we know some things about this triangle. What we know is we know that this is a 90-degree angle. We know this length, and we know this angle is actually 60 degrees. How do we know that that's 60 degrees? Well, if you imagine, I'm just going to switch to yet another color. If you imagine a straight line out here, we've got 1/3 and 1/3 and 1/3. These are all the same. This is 180 degrees. And we know that because of these embedded equilateral triangles. And equilateral triangles all have a 60-degree angles in the corners as well. So a few different ways that we can convince ourselves of that. So with this angle and this length, we can actually find what the W length is with a little bit of trigonometry. So what we're going to be doing is we're going to be doing the radius times sine of 60. Again, I'm drawing with my mouse. Apologize for the mess here. So R times the sine of 60 degrees equals W, and we actually want twice that. So we're going to multiply that by 2 to get this full length. So this is W. So we've ended up with this expression for this distance. So let's plug that back into Houdini. Okay, we're going to go jump back down to our copy and transform. And instead of a specific value here, we can just type in the radius. Wait, how do we get the radius? Well, we can go back to the tube, grab our radius value, copy parameter, and we can do paste relative reference. Now you see this is a little bit more complex than what we had before. I'm just going to finish our expression while we have that in our mind, and I'm going to come back and explain this in a sec here. So we wanted that times sine, and you can see we have the sine function, and there's a little helpful pop-up here. Okay, they even have the example of sine 60. So it returns the sine of the argument, and it's in degrees, so we don't have to convert to radians at all. So 60 degrees, and then we want to multiply that by 2. And when we hit enter, aha, now we have this perfectly transformed series of hexagons. Okay, so this channel, so before when we were just looking at the tube here, all we needed was a reference to rad1. But here, this copy and transform node doesn't have a rad1 parameter, or even if it did, it would be the wrong value. So what we need to do is kind of look it up in a different way. If you're familiar with navigating through folders on the command line or something like that, then this ... is going to be familiar to you. And it just basically means jump up a level. So instead of looking within this node, now we're going to be searching within this geometry context. So we're going to be looking for another node, and slash, it kind of means and then. So first jump up, and then look for tube 1, well that's this node, and then look for this parameter, rad1. So let's go up, tube 1, rad1, that's the parameter that we want. And we could even go up further if we had stuff in other objects. We could go ... slash ... that means first look up in this geometry level, then go up a level further, and then we would specify, for example, the ground object, and then we would specify, for example, the grid node, and then we would specify the size parameter or something like that. So you don't have to understand what this reference is saying. You can just copy and paste stuff and it will give you the right relative reference, but I'm in the business of understanding. I like to understand why things say the things that they do, and that's the reason why. Okay, so if we click on the translate again, we can see what that value evaluates to. So that was pretty close to 2.5. It's a little more precise. So we've copied in the Z direction. Now we basically want to copy all of this in the X direction to create our grid. So we're going to make another copy and transform, wire it up, and click on the blue flag here. And we want to move this over in X. How far do we want to move that? Well, we kind of actually want to move it over this way and also a little bit down. So actually, so to make this a little bit easier, I'm just going to turn on end caps. And that's going to make it a little bit easier to see how things are lining up. So if we kind of wanted to do something like, I'll actually back this up a little bit. So kind of something like that, right? That's going to be tiling. So we're going to need a value in here and a value in here. All right, let's jump back to our math sketch and try to figure out those values. First off, we're wanting to figure out how to move this down. And actually this one's pretty easy because it's just our original W to get from this point to this point, right? So we're just moving it half as far as we did for our original Z direction. So that's just sine of 60 times the radius, like last time. So just as a reminder, so this is our radius. Here's our triangle. And we also need to, in X, we need to move it over. Let's go back, let's do a different value here. We want to move it over this much, right? So that's kind of, we can break it up. So that's this far. So that's our radius, right? From the center to a point. Plus, well, this distance is the same as our radius, right? Because of that equilateral triangle, we knew that this is our bond length, right? Our bond length is the same as the radius. So we just need half a radius here. So basically, we're going to be moving it a full radius and a half radius, or in other words, a radius times 1.5. Now, if you're thinking, I would never have seen that if he hadn't drawn that out and shown me that's what the relationship was. Well, you're not alone, because I didn't see it the first time that I was making this hexagon grid, and I ended up calculating some kind of cosine of this, and in fact it ends up being the same because I actually ended up calculating the sine of 30 degrees, and it turns out the sine of 30 degrees is just 0.5, and that was the 0.5 component of this thing anyways. So this is the simpler version, but the trigonometric version works just as well too. So let's translate that back into our expressions. So here we're copying this in the X direction. And for, what did we say for the translate X? We've got, we can do paste relative reference. So again, this is our tube radius times 1.5, boom. And here we have our paste relative reference times the sine of 60, right? There we go. And now we've got our perfectly tiled hexagon grids, and we can just increase the number of that, and it's going to go on. We can do 10 of those and turn off here. We've got perfectly tiled hexagon grids. Because we've set this all up relative to the original radius, all we need to do if we wanted to change this radius, and it all just stays perfectly working like we would hope. So I'm going to turn off the end caps again because we don't need them. All we need are the points here. And in fact, if you look at these point numbers here, it's a little hard to see, but there's overlapping points. And that's because when we're copying something over, then we get these overlapping points. It turns out all we really need are points 6 and 7 from the original. So I'm going to do 6 and 7. Instead of deleting 6 and 7, I'm going to delete non-selected. And we're left with a tileable grid of hexagons as well with no overlapping points. And now we need to roll it up into a tube. Okay, so we've got in Houdini various deformers. One of them is called the bend deformer. And I'm just going to show what that how that looks like on another tube here. I'm going to create a tube and plug that into the bend here. Go back space 1 to go back into this view here, perspective view, and the tube, I'm going to make polygon, give it a bunch of rows here, make it taller, and I'm actually going to offset it here. Okay, so this bend former, if we hit enter, we can get this handle in the viewport, and we can do that and just start bending things, changing the bend angle. But it's not deforming exactly the way that we would want it to. And that's because we need to specify the capture direction and the capture length. This is trying to capture kind of the long axis along the z-axis currently, 1 in the z-axis. And we actually just want for this one to go up in the y. So we're going to put 1 in the y. And the curve length, we can go up to 10, or the capture length, I should say, we can go up to 10. And then if we change the bend here, now you can see it behaving more like you might expect. And that's just going to be bending. Boop, 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 boop. And if we do something like 360, you're going to be bending all the way around into a full circle. Okay, so that's kind of what we want to do with our hexagon grid. So I'm going to just unhook this from here and plug it into here. But our capture regions are not set up properly. So what we want is for this to actually be looking down the x-axis. So I'm going to do 1 in here and 0 in here. And you can kind of see, it's a little hard to see. I'm going to be doing trying to do some navigation here. We can see that's kind of rolling up, which is what we want, but it's not exactly how we want it quite yet. If we wanted to, we can jump into not the right viewport, but the front viewport, and we can kind of see down the axis of our nanotube. And we kind of want to increase the capture length until we have sort of this nice repeating hexagon. And that's a little bit hard to see. And I'll admit that in my original version, I just eyeballed it. And when I was developing the tutorial here, I was really trying to figure out if there was a formula that would work so that our hexagons are going to perfectly wrap around and connect up with each other. And it turns out that there is. And it's basically just, if we paste relative reference, it's our radius times 15. Boom, there we go. Actually, one way that we can see this a little better is if we just grab or make a copy of our connect adjacent pieces thing here. Paste it here, copy and paste with Control-C and Control-V. There we go. And I'm going to turn off this display here. Is that more or less helpful? I'm not sure. So again, it might still be a little bit tricky to see, but we've got hexagons running around this tube in quite a nice nanotube. So I'll admit I did quite a bit of trial and error to figure out what kind of relationship there is between the radius, between our bond length essentially, and this tube. But if we look at the end view, whoops, space 3 to go to the front view, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 full-length bonds, and we've also got 10 half-length bonds because of how the hexagons are kind of staggered, I guess is the right word. Half of 10 is 5, so 10 plus 5 is 15 bond lengths. That corresponds to the radius times 15 to get that perfect capture length to go all the way around 360 degrees. And the number of copies ended up being relevant here. So in our X direction, we had 10 copies. And in our Z direction, well, we can have as many as we want. We could have 5,000 and our nanotube would just get longer and longer. But 200 is okay as a starting point here. Okay, so basically we have our atom arrangement here with, depending on how you count it, sort of 10 hexagons around, which is consistent with the radius of some of the smaller single-walled carbon nanotubes in the literature. And now what we want to do is we want to put that cap on it that we made, our buckyball cap. So the first thing that we're wanting to do is actually sort of trim some of these regions so that we have a nice connection to be made here instead of this kind of edge thing that's happened because of how our offsets have been created. So I'm going to get rid of this connect adjacent pieces, and I'm going to put our display flag back on the bend. And what we actually want is, because we're sitting sort of above the plane and our buckyball is sort of centered in the plane, we want to move our nanotube down half of its height. Here we go, half of our height again. So what I'm going to do is going to put down a transform node, connect it up. Okay, so one additional trick that we can use to move the nanotube down so that it's centered around the origin is by using a function called centroid. And centroid is basically looking at what the middle of that geometry is, and then we could use that as our sort of transform value. So basically it's going to ask which geometry do you want to look at, and in this case we don't want to look at another object's geometry, we want to look at the geometry of that same node, and we can just put in 0 to tell itself to look at your own geometry, don't look at another object's geometry. And then we have some options for X, Y, or Z. We're going to choose D_Y, which is the value for doing the Y centroid value. And now that's moving it up. We actually want to move it down. And if we put our display flag on here, actually just make sure. So we're moving it down sort of half of its height so that we've got that centered in the very center. Okay, so what we also want to do is kind of trim the edges here, again, where we've got these sort of protruding extra bits here. And we can do that with the blast node, but what do we want to blast? Well, I don't want to do a manual selection in this case. What I want to do is specify a bounding region. And we can do that with the group node. So we can specify a group to trim. And in this case, we want to make sure that the type is points. We're going to be grouping a certain kind of points. And we're going to call this group name trim. And instead of this manual selection or this base group, we want to choose the second option, keep in bounding regions. And we get this little box that we can scale up and move. And we basically want to keep a certain region here and trim off the ends. So we want to center this sort of halfway along its length, which seems to be about 250. So we're going to just put in 250 here. And we know that our nanotube is less than 10. So we're going to put in 10 for the X and Y, sort of get this cross-sectional thing here. And basically we just want to move this out. Sorry, there's little arrows here, and I'm holding down Shift to move both ends of it the same way, and kind of shift and drag those out to somewhere around here. If we do space 2 to go into the top view, we kind of want to keep just right up until here. So we're just trimming off this extra cap. So something like 480, and we'll make sure that 250. Is that right? Yeah, that'll be good. So we're just making sure that we're coming here. If we look in here, we're just trimming off that sort of overhanging edge. Sometimes it's hard to see from the top view where those points are sort of ending up. We could trim more. We could just bring it back more, but I think this will be fine. And then what we want to do is we want to use our blast node, drop it down here. Whoops. Getting my nodes tangled up. And we want to choose, remember our group type, we want points, and we want to choose our trim group. And we don't want to delete our trim group, actually we want to delete everything but our trim group. So there we go. So now we've got a nice flat end to our nanotube, and we want to connect our buckyball onto it. Okay, so to actually merge this all together with our buckyball, what we're going to be doing is we're going to take all of this part of our network. You can select all the nodes and move them up, or another little handy hotkey is if you hold Shift and click on a node, it's going to also grab everything that's upstream. And if you hold Control and click, it's going to grab everything that's downstream. So Shift, upstream, Control, downstream. And you can remember that just because Shift is above Control, which is below Shift. And another way to tidy up our network, sometimes I like to do hold down A and click and drag upwards, and it's going to just sort of tidy up everything in that direction. You could all go A and go left. I don't want to do that. So I'm going to hold Shift and click on blast and just bring it over here. And we actually want to just bring it close to our soccer ball, because this was the output where we just had points. We're actually going to be reusing all of the rest of this network. We don't have to duplicate any of that effort. If we just merge the result of this and the result of this together. Okay, so we're going to hit tab, put in a merge, and we're going to drag in first this and then this. And if we put the display flag on here, so we've got our buckyball and our nanotube. And if we rewire this into our atom copy to points and over here into our connect adjacent pieces, if we look at our final result, hey, look at that. We've got nanotube geometry and buckyball geometry. Now it's not joined up yet, obviously, but we're just about to do that. But that's fantastic. We haven't had to make any changes at all to all of this part of our network, and that's part of the procedural nature of building things in this way. Okay, so we clearly want to get rid of about half of our buckyball, so let's do that. I'm going to shift click on here and give ourselves some space and do a blast. And in this case, we could do a bounding box region, but I'm just going to do a manual blast because I know that our buckyball geometry isn't going to change. I'm going to go to points, and if we just go from the side view here, side view, there we go, space F to frame up on it, zoom out a little bit. I think we're going to be doing that side. Actually, you'll notice that when we've made this selection, our display flag has been changed to the node above it, and that's just so you can say, look at the geometry that's coming into this node. What is it that you actually want to get rid of? What I want to have be able to see is not this add node, or not just this add node, but actually our nanotube, to figure out where that is. And there's a nice little way you can do that is by using the template flag, which is the second one over. It's kind of this purplish pink. And if we click on that, then we can see this ghosted version of the result of that node. And you can shift click on other nodes and see as many nodes templated as you want. But then you can also click on it again to get rid of it. The hotkey is E as well. Whatever node is selected gets that template flag. Okay, so I'll set the template on this blast node here, which is the end result of our nanotube, the tube part of it at any rate. So yes, so this is the side of the buckyball that I want to get rid of. So I'm just going to hit enter in the viewport. Whoop, there we go. And it's put in the right points that I want to get rid of here. And if I want to, I can put the display flag back on our end result. And I'm going to drop in a transform node, and we could either move the nanotube to the buckyball or the buckyball cap to the rest of our tube. I think I'm going to move the buckyball, half of the buckyball over. And I'm just going to kind of click and drag. And because it's going to be a little bit slower because it's constantly evaluating all of this as we're dragging it. But the reason I want to do that is I kind of want to bring it until there. We get the bond connections being made. And I know that that's kind of the right distance because we put in our search distance. Actually, we should maybe do this a little bit more precisely. We want this to be our relative reference divided by 2 plus 0.001 for just a little bit of a buffer because it's exactly our bond distance and it might not actually find it. We just want a little bit of that buffer here. So 0.711, but you can do it however you like. That's how I'm going to do it. So we know that we want to bring this a little bit closer, and we could do that even here if we're kind of going, there we go. Just sort of find that threshold for where things kind of join up. In this case, I am actually just sort of eyeballing it. It's not mathematically 100% precise, but neither are the distances between two atoms. So do it how you like. Okay, and that's pretty much our whole nanotube has been created. Let's go back down to our end result here, maybe perspective view. We can go into shaded mode. We've got a pretty nice cap on that and a great carbon nanotube, very long. And again, we could always adjust how much longer we want it to be. We would just have to maybe update this group trim so that it would trim further down. That's something that could be made more procedural if you were going to be playing with that, but I'm happy with where we are for now. So now what we want to do is we actually want to deform this carbon nanotube so that it's not perfectly straight. It's kind of coming up in a wavy line and it's growing from the ground upwards. So what we can do is use something called a path deform, and that's another kind of deformer that we can use on our geometry. And I think it's relatively new. It might be Houdini 18 or 18.5. I'm not quite sure. But first what we want to do is we want to create a curve. So I'm going to go into space 3, maybe our front view, and I'm going to put down a curve node somewhere over here. Actually, we should update the name of this. This isn't our buckyball anymore. It's our nanotube. We call it our straight nanotube because we're going to be deforming it downstream from this. Okay, so we're going to call this is our path, our nanotube path. Okay, so we're going to do a type NURBS, and we're going to be in our front view, start drawing down points, and we're going to start clicking pretty close to the origin here and start clicking out. And we'll make it about, we don't want to make it quite as long as our nanotube, maybe around 250 or 300 in length. That'll be good. So you can hit enter here. And if you're not seeing the curve being drawn, make sure that your display flag is on the curve itself. And we can actually put the template flag on the nanotube if we want to see that at the same time. Okay, so we've got this nanotube path, and then we're going to put down path deform. And it's got two inputs. One is the geometry to deform, that's this guy here. And it's got a spine curve, that's this one here. So we put that in here and put the display flag on it, and hooray, we've got our nanotube up the curve. But there's a couple of issues here. One is that the buckyball or the cap end is right at the bottom. So we're going to go in here and change a couple of the parameters here. I'm going to untemplate this because we don't need that anymore. So we're going to first reverse the curve so that the top of it is here. And now it's kind of sticking through the ground. So what we can actually do is under map and deform, the end behavior, we can clip it. And that's just going to remove anything that's at the bottom of the curve. So we know that we're kind of locked to the ground. And the other thing that I want to do is actually back on the original path. I want the first CV to be exactly at the origin. So you can see here there's a list of a whole bunch of points. These are the point positions of each of the CVs. I want to make sure that the first one is 0. So I'm just going to edit that to be 0. And that's going to be right at the origin there. And one final thing on the path deform, this isn't going to be relevant right now, but if we actually start animating the growth of the nanotube, which is what we're going to be doing in the next video, I actually find that changing the curve up control to the Z-axis is going to prevent the nanotube from doing kind of a glitchy spinning thing where it's kind of like quickly jittering and shuffling around its axis as it grows. And the reason for that is the up control, if it's Y, that's kind of close to the same axis that its primary direction is, if that makes any sense. And having those two axes too close together can create some kind of instability in the sort of the rotation that's being calculated. So I'm going to put it to Z. I'm pretty sure that X would also work if you wanted to try that. Cool. And let's drop down a null, another null at the bottom here. It's kind of, again, maybe we'll call this out deformed nanotube or curvy nanotube or whatever you want to call it. And that's kind of our final result for this video. One thing to note is that the path deform is fairly computationally intensive, and that's actually one of the big reasons that we wanted to pack our atom spheres and our bond geometry into individual primitives, packed primitives. So if we took these, if we shift select both of these and hit B to bypass them, it actually takes quite a while for that actually to cook. Cooking is the name given to computing the network here. So it takes a while to cook this network. And if we wanted to go here and sort of change the position of any of these curves, it's going to be very slow to update. If something's taking too long to cook, you can always hit escape to cancel cooking, and you'll see that these red flag here. Cooking was interrupted, so it's not actually going to show you anything because you didn't let it finish. Let me finish. So I'm going to re-enable these by hitting B. And then if you go back here to here and hit enter in the viewport, then you can actually grab these. And by having packed the atoms and the bonds, it's much more responsive. I'm getting like 6 frames per second, which isn't insane, but it's very interactive and workable. And that's it. That's our nanotube on a curving path. I know Houdini can seem pretty scary at the beginning with all these complicated node networks. We've got a pretty interesting result out of not too many nodes. There's only maybe like a couple dozen nodes here, and we've done some pretty interesting things making this scientifically accurate carbon nanotube here. It's a good idea to kind of go through the node network and name your nodes and sort of document your process. That'll tell you when you're revisiting a node network later, or if somebody else is, what the actual reason for having these nodes is, and it'll help us to do a little bit of a recap here. So we made our hexagon, and we got deleted some geometry from it, the redundant stuff. I'm going to zoom in a little bit. Then we copied that hexagon in the Z direction, X direction to tile it, and then we rolled it into a tube. We sort of centered the in Y. We created the trim group, and we trimmed the ends of that nanotube. And then we had our soccer ball. In the previous video, we deleted the color. I know I like the American spelling for that, even though I'm not American. We deleted the primitives. We deleted half of it, and we aligned it with the tube, merged it together. Then we have our atom sphere. We have a scale multiplier. We packed it into individual atoms as sort of atom primitives, copied the atoms to the points. This is our atom primitives group. And on the bond side, we sort of got our bond connect primitives and did a bond polywire. It's fairly self-explanatory there. We packed the bonds into individual fragments or packed primitives. We've got our bond prims group here. Merged the atoms and bonds, color it black, and there we go. We've got our straight nanotube. We've got our tube path to form. There we go. So we kind of named everything so that if we come back to it later, it'll be like, why did we need to do this or that? And it kind of gives you a little bit of a reminder of what you were actually doing. So thank you so much for joining me for another part of this nanotube mini-series. In the next part, we're going to create some animation so our nanotube can actually grow up from the base, which is going to be pretty cool. We'll learn a bit about keyframe animation and maybe do a little teeny tiny bit of coding. Don't worry, it'll be good. It'll be fun. I'll explain it. So once again, if you learned a few things here, thumbs up and comments are very much appreciated. If you're having a good time in Houdini and want to share a little bit of that joy around, feel free to share this tutorial series with a friend or a colleague. The more the merrier. If you haven't yet, please consider subscribing to Making Biocinematics so you can see when new tutorials are posted. If part 4 is already published, you can join me in the next video by clicking over here. I think I got it right that time. But sincerely, thank you so much for watching right to the end of this video, and I hope to teach you some more things soon. Bye.